Okay, let's compute an MLE. For the following situation. Theta is some positive number. Okay, so what words would you use to describe the common distribution of the xi's? The density is 1 over theta on the interval from 0 to theta. And that means they are uniform. So if theta is unknown, what's the, yeah?
Is that 1 times 1, or what is that?
Where? Here? Oh, yeah, this is, yeah, this is the indicator function. This means the function that's 1 when x is between these two numbers and 0 otherwise. So maybe it's more common to write this, I guess. Okay, I think I should have written it that way. So how can you compute the maximum likelihood estimator here? Let's write down the likelihood function for the sample. So there's the likelihood function. We want to maximize that. Let's maybe draw a picture of our data, or the random variables. Since they're all uniform on the interval from 0 to some positive value theta, we know the xi's are all bigger than or equal to 0. So if you recall this notation, I can plot the order statistics this way. Okay, and we're given these guys. So x superscript parenthesis 1 was the smallest of the random variables x1 through xn. x2 is the next smallest. This thing is the largest, right? Okay. As you can see, this is the largest. Okay. So this set of points is the same as this one. It's just that these, if I reorder these and write them this way, okay, that's what I get. Okay, so let's think about plotting L as a function of theta, starting at theta equal to 0. What's the value of L in here? Well, what's the value of this function when theta is less than xi? 0, right? So this would be 0. So we're taking the log of, and the log of 0 is pretty small, minus infinity. Okay, so we'll put minus infinity here. Okay. So in here, this L is minus infinity. When we get to x1, one of these things becomes 1. One of these becomes 1. But the rest are still 0. So we still get contributions log of 0, which would be minus infinity, plus something finite, which would still be,
Minus infinity.
yeah, minus infinity. So this will be minus infinity until when? No, not forever. Don't be so pessimistic. Till here. And then it jumps to something. What does it jump to? Then all of these will be 1. So we'll add up log 1 over theta n times. So we'll get n log 1 over theta. It'll jump up to n log 1 over theta. That could be a positive number, could be negative. Depends on whether theta is bigger than 1 or less than 1. Which do you prefer? Let's take theta bigger than 1, then it'll be a negative number. So we'll jump to n log 1 over theta. And from then on, it'll be, as a function of theta, it'll be n log 1 over theta. And what does that do as theta increases? What is the graph? N log 1 over theta, is that increasing or decreasing with theta? What about 1 over theta? Does that increase or decrease as theta gets bigger? Decreases. And log is what kind of function? Increasing, right? So if 1 over theta decreases, log 1 over theta would decrease. So what does the graph do from there? It goes down. Never reaches minus infinity, but it tries to rejoin its old friend. It goes down like that, okay? So this is the graph of L of theta. Minus infinity until the maximum term among the random variables x1 through xn, and then it decreases. So where is the maximum? Where does the maximum occur? Yes. So what's the maximum likelihood estimator? Okay. Without writing down any formulas, unless you insist, let's consider the discrete analog. Okay, what kind of situation might this be? Here's my favorite statistics story. It's wartime. You're a spy. You're behind enemy lines. You're supposed to report back how many tanks the enemy has. The enemy is dumb enough to put a number on each tank as they're produced. So you run around the countryside reading off the numbers on the tanks. So when the enemy made its first tank, it put the big number 1 on it. When it made its second tank, it put the big number 2, and it kept doing this. So you can see the numbers on the tanks. What number would you report back? Number of tanks you've seen? Pardon?
The largest number you saw.
Yeah, that's what this says. If the analog for discrete random variables holds, you just report the largest number you saw. That's one number. You don't have to report the gaps between them or how many you've seen. So if you just see one and it had the number 673 on it, you'd say, well, my guess is they have 673 tanks.
aren't you assuming that they started it, they
What-
indexed it at 1? And
Yeah, so you know that. They started at 1 and
Okay. How would you?
how would you come by that information? You heard it in a bar one night. You know this saying, loose lips sink ships? Yeah, so. Okay, so why don't you try to work that out, that the maximum of these guys is the MLE for capital N. Okay, so that's kind of strange. You collapse all the information you gathered down to just one number. Is there more information to be gathered or derived or gleaned from the data? And this is the question of sufficiency. So let's recall what sufficiency means. Yeah, so we'll start with this. Oops. Okay. Okay, so statistics are functions of the data. So we have that function of the data there, capital T of x1 through xn. It's a sufficient statistic for theta. If the conditional distribution of the random variables given the value of that statistic does not depend on theta. So there's no more information to be gotten from the probability distribution of these random variables once you've conditioned on the value of capital T. No, there's no more information left in the data, more or less, once you know about the parameter, once you know the value capital T. So last time we did an example with Bernoulli. I'll just remind you what the result was. Then X bar was a sufficient statistic for P. It turns out it's an unbiased estimator as well. And we check the conditional distribution. What is that? And as you can see, this has no mention of P. Okay, that's what. And because of this has no dependence on P, X bar is a sufficient statistic. Let's take this density. And now we have two parameters. And we can think that of this statement as being valid for theta being a one-dimensional parameter as well as being a vector. Theta could be a k-dimensional vector, and then t could be a k-dimensional vector as well. We don't have to be in one dimension. So here, how many parameters do we have? We have two. So we might think about theta as being the vector mu sigma, and then we'd want t to be a pair of functions, t1, t2 of the data. Okay. So let's suppose we have some data. And let's write down the joint density of an IID sample. From this distribution. Well, the joint density would just be the product of the individual densities. Like that. And I could expand the square there and write the individual sums this way. Yeah. Oh, right. There's an n missing here. Yeah. So does this suggest any sufficient statistics? Well, I think it suggests let's see why. We'll write down a theorem that'll explain why. And this is called the Factorization Theorem. Yeah.
Do you have another marker?
Yeah, I actually, does anybody have another marker? I do in my car. What we could do today is have our break early. Okay, so this abbreviation means necessary and sufficient condition. It's much easier to write NASC than write necessary and sufficient condition. So what does it mean, necessary and sufficient? If T is a sufficient statistic for theta, then the joint density can be factored this way. And on the other hand, if the joint density can be factored this way, then T is a sufficient statistic. We'll use the theorem only probably in the direction if the density factors this way, then the statistic T is sufficient. Before we prove it, let's apply it. And you probably have a difficult time reading this one too. Okay. Now this is a function of T1, T2, and the parameters mu and sigma. The only way that the variables appear, or the data appear, is through the function, the value of the functions T1 and T2, right? T2, T1. So let me write out, cross out, it suggests by the factorization theorem the pair T1, T2 are sufficient statistics. Again, the only way the data appear in combination with the parameters is through these two functions. Here's T1, here's T2. Okay. So do I need to write this out more explicitly? Okay. See, only the functions of the data appear there. Okay. And so this parameter and that function t could be vector valued as well. And so we're applying it in the vector case, the two-dimensional case. Theta is the vector mu sigma squared. Capital T is the vector T1, T2. Okay. Let's do another one. Let's consider Poisson. And lambda is unknown, of course. I think we computed the MLE for Poisson, and it was x bar. Is it sufficient? In other words, is there any more information in the data that we can use to get a better approximation of lambda? Well, let's try to use the factorization theorem. The joint density is that? For an IID sample, right? Okay, let's rewrite this a little bit. Think about the product of these things. That would be lambda to the sum of the little xi's. And then down here we have the product of the xi factorials. And we have this thing multiplied by itself n times. And now let's look what the factorization looks like. You try to separate out the parameter with some function of the data, and then all the other bits about the data have to be over there. And let me be a little more careful here. This h does not depend on theta. It can only depend on the x1 through xn. Right. So where are the appearances of the parameter here and here? So let's separate those. And then here's the other stuff. And there you have it. This part is what? That's the g of, I guess, n times t, right? But it would be g of t, I guess. G of n times t is a function of n times t is also a function of t. So this part is the g, and this part is the h. Then see this h part has no lambda dependence. There's no lambda there. It's all here. And how are lambda and the data interacting in here? Only through the sum of the data points. So this says t is a sufficient statistic. So the answer here is yes. By ft. And what's ft? Factorization theorem. Okay. Yeah.
But our t is just x bar, right?
Yeah. But this is a function of So is this a function of t? It's lambda to the n raised to the t. So maybe this is worth mentioning. Any function of a sufficient statistic is a sufficient statistic. If it's, I guess, let's say, is it true for any function? Let's say any invertible. Just to be careful. K is a function which we can invert. So this defines, this is a well-defined function here, g of k inverse of s and theta. That gives me a function of s and theta, right? What variables do you see here? S and theta. So I defined m this way. It's g, which I already have, of some invertible function. Like here, what did we use? Our t was x bar, right? Which is 1 over n, sum of the xi's. So here we had, here I'm claiming that if this is a sufficient statistic, then 1 over n times it is also. If I multiply, if I take the function multiplication by 1 over n, that's invertible, right? So what happens when I put s equal to k of t in here? If I put k of t in here, what do I get? What's k inverse of k of t? It's t. So I get g of t theta, right? Okay. So any invertible function of a sufficient statistic is a sufficient statistic. So if you find a sufficient statistic and add a constant to it, that'll also be sufficient. If you multiply it by a number other than 0, that'll also be sufficient. Okay. If you take the log of it, that would be sufficient. If you exponentiate it, that would be sufficient. Okay. So can we answer this question? Is the maximum of the data sets, say the data set, a sufficient statistic for theta? We found it's the MLE. Do you think it's sufficient? Well, what tool do we have for determining whether anything's sufficient or not? We can use a definition, or we might use a theorem. Can we use this theorem somehow? Oh, here I should have put mu and sigma squared. I rewrote that. I forgot to add those. Okay, well, let's write the joint density for this. Right? And what do we have to do? We have to see if we can write that as a function of just the statistics and the parameter, and then plus times a function of all the other data. Okay. Now let's consider maybe I can factor out the theta there. Oh, and I rewrote it this. This means that 1. Okay, this means 1. This is 1 if xi is between these two numbers, and it's 0 otherwise, right? Yeah.
Why is it theta to the negative 1 again?
Okay, well, it's uniform on the interval from 0 to theta. Do you remember what the density was on the interval for the uniform random variable? Okay, so let's integrate this function from minus infinity to infinity. This is constant, right? We integrate an x. So I pull that out of the integral. So I integrate this from minus infinity to infinity. It's 1 between 0 and theta, and 0 otherwise. So this would actually be the integral from where to where? From 0 to theta, right? Because off that interval, this function is 0. So if I integrate 1 from 0 to theta, what do I get? That's the area of a box of height 1 and length theta. So it'd be theta times 1 over theta. So the integral of this would be theta multiplied by 1 over theta. That gives me 1, which is a density. Okay. Answer the question? Okay, good. So we have that. Can we write this as a function of the largest data point? And here, all our x's will be bigger than or equal to 0. And theta? Oh, well, maybe not. Let's see. And then h of x1 through xn. Okay, this means the maximum of all of them. So I erase that restriction on these being non-negative. I can take care of that. Can we do this? Well, let's look at this thing. What's the value of this product? We're taking a product of what kind of numbers? N of them, but what are they? This is either
1 or 0.
Yeah, 1 or 0. When is it 0? If some xi is less than 0, or if some x is bigger than theta. Otherwise, it'll be 1. So I think I can write it this way. wrote something here. Let's see if this agrees with that. What if all the x's are between 0 and theta? What do we get? If all the x's are between 0 and theta, this would be 1 for every one of the x's. So this product would be 1, and it would get theta to the minus n. Would we get that here? If all the x's are between 0 and theta? This one says all of them are bigger than or equal to 0. What does this one say? The largest one is less than theta. So what about the rest of them? They all have to be less than theta. So this would be 1, this would be 1, you get theta to the minus n. If one of the data points is outside of the interval from 0 to theta, what happens? If it's to the left of 0, this would be 0. If there's one to the right of theta, what would happen? Then the maximum one would be to the right of theta, and this would be 0. Okay, so this function and this function agree, and this function has that form. Here's the statistic. This is a function of the xi's. It's the maximum of them. This is the t. And it has the theta in there. Does this have any theta? No. So this is the h, and this is the g of x and theta. Okay. So that says that the maximum is a sufficient statistic for the parameter theta. So in the case of, if you apply this to the discrete model, and you reported 673 was your estimate for the number of tanks they had, and the general asks, well, why do you say that? And you say, well, that's the largest number I saw. And he asks, well, is that a sufficient statistic? You think generals don't know these things? Okay, well. Do you know that Napoleon Bonaparte knew Fourier analysis? He's a very good mathematician. So some generals do know these things. And you would say, yes, of course it's a sufficient statistic by the factorization theorem. And he'd say, yeah, I forgot. But it's kind of amazing that the data set could collapse down to one point, or just one element. I mean, you could have seen 10,000 tanks. So maybe the number you saw was, the largest number you saw was 21,382. And that one number captures all the information there is in the data about the total number of tanks there are. Okay. So this is a nice application of the factorization theorem. Another application is to identify a certain family of densities called exponential families. let me change this to k of xi here. Now this means that the individual densities are given by this, some function that looks like that. Okay. And now when I take product, I can exchange the exponential and the product by putting a sum up here over the i's, right? So far, so good? Or to show off my Chinese, 对不对? Okay. And now let's separate this part out. I'll write it as a product of two exponentials. One that has this function of the data, and then the other that has the sum of the xi's. I separate this part out because it has no theta dependence. And let me point that out explicitly, no theta dependence for the function s. Okay? So if the individual density has this form, then the joint density will have this form. Okay, now remember what the factorization theorem said. T would be a sufficient statistic if you could factor the density into a function that depended on the data only through the statistic and the parameter, and then some other function that depends only on the data, but not at all on the parameter. And now that's what we have. This is a function that depends on a function of the data and the parameter, and then some other function depends only on the data, no parameter. So this is the h. And this is the g. And what would the sufficient statistic be then? T of x1 through xn would be the sum of the xi's, or k of xi's. Okay?
Why is it not e to that sum?
Here? So this is a function. This is a function of how does the data appear in this function? Only through this sum, right?
Yeah.
So it's this function, this sum, that's the sufficient statistic. It's this combination of the data that's the sufficient statistic. Okay. This is a function of what? The theta and that function of the data. Okay. Here's that function of the data is the sum and the theta.
I was just saying because you have e to that power.
Yeah, but that's so.
Is that
So what's okay? Let's write it down. G of t and theta would be e to the c of theta, t plus n d of theta. Okay. This is a function of t. That's going here. And theta. There are two things here that depend on theta. One, theta, a function of theta is multiplied by the t, and one where there's no t dependence. Okay, so this is a function of the data through this and the parameter, and this is a function only of the data, no parameter. So by the factorization theorem, for an exponential family, this sum is a sufficient statistic. Or this is the thing that appears here. Okay, we already saw this twice. Let's look over here. The joint density for IID normals with mean mu and variance sigma squared looks like this. This is the joint density for normal with mean mu and variance sigma squared. It has this form. These could be vectors, by the way. This could be inner product between a vector c and a vector k. In this case, maybe I'll write it out. So far, so good. Okay, well, all I did was I multiplied this part here through by the minus 1 over 2 sigma squared. This times this gives me this. This times this gives me this part. This times this gives me this part. And then I put this in the exponential by taking e to the log of it. I get this. Okay? And I can rewrite this as e to the c of mu sigma squared times k of x1 through xn plus d of mu and sigma squared, where c of mu sigma squared is the vector minus 1 over 2 sigma squared, mu over sigma squared. K of the data is the first component of this vector is a sum I equal 1 to n x sub I squared. The second one is a sum I equal 1 to n x sub I. And d of mu and sigma squared is minus n mu squared over 2 sigma squared minus n log 2 pi sigma squared. Okay, and so this is an inner product here. That means we multiply first components together and second components together and add the result. And that gives us what's in this line here. And this part is just a function of the parameters alone. And so if we look back over here, maybe at this middle line here, this part is what? That's the c. We have the c of mu sigma squared, and then we have maybe I could call this sum I equal 1 to n k sub I of xi, k1 of xi, sum I equal 1 to n k2 of xi, where k1 of x is x squared, k2 of x is x. So we'd have a vector product here, c1, c2 times k1, k2. That's what we get here, c1 times sum of the k1s, c2 times sum of the k2s. Then we get this n d of theta. Oh, I'm sorry. I shouldn't have the n in here. So this should be n times d of mu sigma squared there. Okay. And what about the this part here? Does that appear in that example? No, it's 0 for the normal. So the normal is an example of an exponential family. And that means what? Exponential families have this as a sufficient statistic. So that means that the pair, sum of the xi squares, and some of the xi's are sufficient statistics for sigma squared and mu. Okay. Okay, in other words, there's no more information in the data to be had about these two parameters than in this pair of functions of the data. Can't get any more information out of the data than that. What about the Poisson? Is that an exponential family? Well, let's rewrite this bottom line here. I think I got that right. This part, how do I get that to look like this? Well, I write lambda as e to the log lambda. And it's raised to this power, so I have to multiply that by the log. That gives me this part. This is, well, I just wrote it again. And then here, I write this as e to the log of this thing, right? A is e to the log a. So what's e to the log of this? Well, I take log of this, the minus 1 comes down, that gives me this minus sign. I get a log of a product. How do logs get along with products? They become sums. They convert products to sums. So it becomes the sum of the log of this. That's that. So does that have that form? Here's the k. This is the c of lambda. Here's the d of lambda. And here's the sum of the s of xi's. So this is an exponential family. So that means this is a sufficient statistic for lambda. Can you think of any other exponential families? What do you think might, in your repertoire of distributions, what one do you think might be? Well, how about exponential? Let's check exponential. Is the exponential density an exponential family? Well, it better be, I think. Joint density then of an IID sample Okay, so does this have the form of an exponential family? Well, maybe. Let's look at this. So theta is lambda, right? Is there a function of lambda times the sum of some function of the data? Yeah, the k of x would just be x. Well, I'm sorry. Theta is theta. This is c of theta. C of theta is 1 over theta, or minus 1 over theta. And this is d of theta then is minus log theta. So c of theta is minus 1 over theta. K of xi is xi. And d of theta is minus log theta. And then what's capital S? S of xi is 0. And so the exponential density for IID exponential random variables is an exponential family, and therefore a sum I equal 1 to n xi, capital Xi, is a sufficient statistic for theta. But is that the one we want to use to estimate theta? Why not? What's the expected value of the sum? Yeah, and the expected value of xi would be theta. And so the expected value of that sum would be n theta. So we'd be off by quite a bit. So we should use x bar, right? We should use x bar. Is that also a sufficient statistic? Yes, because it's an invertible function we've applied to the first one, right? And that would be the one we want to use. Any other examples you can think of exponential families? Let's try gamma. Here we'd have two parameters, lambda and alpha. We get lambda to the alpha over gamma of alpha to the nth power. And what does the individual density look like? let's convert this. Remember, x is positive here, so I can take the log of this. So I can rewrite the density this way. And if I evaluate this now at xi, and take the product of this, product and exponentials, when I take products, it's the same as taking sums in the exponent. We get that. So up here we get e to the minus lambda sum I equal 1 to n xi plus alpha minus 1 sum I equal 1 to n log of xi. And just to put it in that form, I should take e to the log of this. And that looks like an exponential family. So sum of xi's, sum of log of xi's is sufficient for alpha and lambda. So if you want to predict alpha and lambda, and you use some invertible functions of these, there could be no more information in the data than is contained in these two functions of the data points. And so the gamma is an exponential family, and we can derive sufficient statistics then that way. Okay. Okay, and let's go back to the factorization theorem for a minute. Let's suppose our joint density factor is like this. And now let's suppose we want to find the maximum likelihood estimator. So let's suppose we can factor our joint density this way, and we want to find the maximum likelihood estimator. How would we do that? How are they related? Well, suppose t is a sufficient statistic. For the unknown parameter theta, which could be a vector. Then the factorization takes place. The joint density Okay, now let me warn people, I don't like it when you leave early unless there's a very good reason for it. So I just noticed somebody else left and I heard 2 people leave. No, I don't want, that's one thing I don't like. Okay, maybe you can tell the other people that left early that I don't appreciate that. Okay, so we can write this way. Okay. And how do you take the maximum likelihood estimator? You form the log likelihood function. And the log of a product is the sum of the logs. So we get this. And now we differentiate with respect to theta to find where L takes on its maximum. We differentiate with respect to theta. We get the derivative with respect to theta, g of t of x1 through xn and theta divided by g of t of x1, xn, and theta. So what happened to the h?
It's constant.
Yeah, right. There's no theta dependence there, so its derivative is 0. We set this equal to 0. So we have to look for solutions to this equation. So what does that say about the dependence of if theta hat's the MLE, it satisfies this equation. So how does the MLE depend on the data? Well, how does the MLE depend on, what does it depend on? It depends on t. It depends on the data only through a sufficient statistic. So that means that the MLE is a function of the sufficient statistic. MLEs are functions of sufficient statistics when they exist. So if you have a sufficient statistic, the maximum likelihood estimator has to be some function of it. Okay. So that's how sufficient statistics are related to maximum likelihood estimators. Now, did I assign 17, 18, 19, 21, 23 from chapter 8? These are involving beta densities. Was it assigned or not? Not? 17, 18, 19, 21, 23. 21 is the only one? Okay, well, let's look at 17 then. 18, unless you'd like me to do 21. I think you probably can do that, huh? Yeah, 21's a good one. 21's a lot like the, I think it should be like the uniform. Have you solved 21 yet, anybody? Do you want to talk about it a little bit? Okay, let's talk about number 21 then. Okay, here x1 through xn are IID. And the joint density, I'm sorry, with common density function, f of x given theta equal e to the minus x minus theta, where x is bigger than or equal to theta. And 0, of course, when x is less than theta. Okay, so what's the expected value of x? We integrate the density against x from theta to infinity. Why theta? I'm sorry, this is theta here. Because the density is 0 when x is less than theta. And we can factor out e to the theta, integrate theta to infinity x. Or, yeah, let's do it that way. E to the minus x dx. And then we integrate by parts. Like that. And we get e to the theta u times v. That would be x times e to the minus e to the minus x, evaluated between theta and infinity, minus integral from theta to infinity v du. Well, there's a minus sign with a v, and there's a minus sign here. It becomes plus. E to the minus x du is dx. So this is e to the theta. At infinity, this becomes 0 because of that. At theta, it becomes theta e to the minus theta. And then here we get integral of e to the minus x is minus e to the minus x, evaluated between theta and infinity. And we get e to the theta.
Why is not negative theta?
Where? Here? Because we subtract at the bottom end. Okay. Theta e to the minus theta. And here we get plus e to the minus theta. And so this becomes theta plus 1. So the mean is theta plus 1. So this is our function of the parameter. It's theta plus 1. So what should be the ME? It would be x bar plus 1. The sample mean plus 1.
Minus 1.
Oh, yeah, minus 1. Thanks. This would give you theta plus 1, yeah, and then you want minus 1. Theta bar minus, x bar minus 1. Thank you. Okay, and then it asks for the MLE. It says, don't differentiate before thinking. Well, that's good advice always. Let's write down the joint density. And here I should have the indicator, times indicator, xi is bigger than theta. Right? Because otherwise, the density is 0 when xi is less than theta, so I have to throw that in here. Okay. That's why differentiating becomes a little troublesome here, because is this function of differentiable function of theta? This one? If I vary theta here, it's 1 until I reach xi, and then it jumps down to 0, and it's not even continuous, so it wouldn't be differentiable at xi. We saw a situation like this earlier when we did the uniform, right? So what is this? What's the value of this? Well, this thing is either 1 or 0. So this thing is this product term here. The ith product term is either this or 0. Okay. And then what do we want to do? We want to find the maximum of this in theta. I find the maximum of this in theta. And this part's positive, so the maximum will be, could the maximum be 0 when the function's 0? This will be 0 sometimes, right? When will it be 0? If any of the xi's is less than theta. So in order for this to be positive, all of the xi's have to be bigger than theta. In order for this to be positive, all the xi's have to be bigger than theta. Okay. In other words, the minimum has to be bigger than theta. This means the minimum, the smallest. If you weren't in the class last semester, you might not have seen this, but these are the order statistics. Remember, this is the smallest order statistic. Okay, so all of them have to be bigger than theta. Otherwise, if you took log, what would the value of the log likelihood function be if one of the xi's is less than theta? It would be minus infinity. So that couldn't be the maximum of the log likelihood function. So now let's plot the data points. And think about what happens as theta is increasing. Theta is going this way, and we're going to graph L of theta. And if any one of these is less than theta, then the log likelihood function is minus infinity, because if the smallest one is less than theta, then that product will be 0, and the log of it will be minus infinity. So if I put minus infinity down here, the log likelihood function looks like this. It's minus infinity until I get to here. And then it jumps to, what does L of theta jump to? It jumps to that value suddenly. And then what happens is theta, maybe I could rewrite this as e to the minus sum I equal 1 to n like that, right? Okay. Is this correct? This thing is this. And now here the coefficient of theta is positive, right? And which way are we going with theta in this picture? We're going that way. This is what kind of function of theta? This one I've written here is an increasing function of theta, right? So if I go backwards, what's it going to do? It's going to decrease. So roughly speaking, this thing jumps up to here and then goes down, right? Because it's increasing. So if I go backwards, it goes down. So where does the maximum occur?
X1.
Yes, here. So the MLE is theta hat equal to the smallest, well, let me go to random variables. The first order statistic, the smallest of the x's. Okay. Well, I have a haunting feeling that the book uses this to denote the largest. This one. Does it mean the largest in the book or the smallest? Smallest? Okay, good. Otherwise, you have to reverse the. But defined that way, this is right. Okay, so the MLE is this. Okay, now we should find a sufficient statistic for theta. Okay, smallest? Okay, good, good. Now what about a sufficient statistic for theta? I'm sorry. I ran out of room here, but I can rewrite the density this way because the density's the joint density because the density is 0 when the smallest is smaller than theta. So I put this here, indicator theta to infinity of the smallest. And I can rewrite this as e to the log of the indicator theta to infinity of x of 1 plus n theta minus the sum I equal 1 to n xi. So is that of any help? Does everybody agree that that's correct? See, I just wrote, this is the number a. I wrote a as e to the log a. And interpret this as being 0 when that's 1. Because log of 0 would be minus infinity. What's e to the minus infinity? 0. Okay? So can you read off from here what a sufficient statistic for theta would be? Well, this is an exponential, right? So is it an exponential family?
Yes.
How so? What's the, well, it doesn't quite have this form here, but if I had some function here, k of x1 through xn,
It's not.
then that would still be exponential, yeah. But it doesn't have to be a sum of the data here. It could have a, so let me say expanded sense of exponential family. The joint density has this form. Okay, and let's go back to the factorization theorem. With this plus here, I could write this as a product of e to that and e to this, right?
Yeah.
So the first exponential is this guy here, where k is t. And the second one has no dependence on the theta. Okay. So in this case, k is a sufficient statistic because that's the factorization you need here. Okay. And we have that here. Here's our k. In fact, this could be k of theta. I could even do the following. Have this depend on theta as well. I could have the k depend on theta. Well, now let me leave it this way. So what's a sufficient statistic here? x1 is a sufficient statistic. How can we, this is the factorization. Let me just apply the factorization theorem here to this. Let me not try to force it into an exponential family. G of x, g of t and theta is e to the log indicator 0 theta of t. And h of x1 through xn is e to the minus sum of the xi's. Okay, this is the g. The h is e to this. So I've factored the joint density into a function of some function of the data and the parameter, and then the data. Okay. So as I say about this thing here, by the factorization theorem, this is a sufficient statistic. Okay. So I didn't need to do all that extra stuff about exponential families, but this does not have to be a sum of these. It could be a function like this. So, but I'll go to that next time. So here we factored it, and so the minimum is a sufficient statistic for theta. Okay. All right, that's it for today. Is it okay? You look a little.
I was just wondering about 0 to theta or theta to infinity.
Oh, yes, yeah. Theta to infinity, sorry. Yeah, theta to infinity. So this is a lot like the uniform thing that we did at the beginning.